Hello, everyone. Today, I will be presenting our paper entitled HARP-Net, which stands for Hyper-Autoencoded Reconstruction Propagation for Scalable Neural Audio Coding. It is a collaborative work between Dr. Keane, Dr. Beack, and myself, Darius Petermann. So our main motivation relates to the fact that audio coding is being mainly addressed through digital signal processing methodologies, as well as domain-specific knowledge. Which leads us to think that this field could also be approached from data-driven and deep learning approaches as well. Our lab has been focusing on this issue for several years now. Some of our work also tackled the idea of neural audio coding from various different fronts. Last year, Kai and co-authors presented an approach incorporating a perceptually motivated loss towards neural audio coding. Earlier this year, Yang and co-authors proposed the incorporation of source separation paradigm towards neural audio coding, where priors related to the nature of the sources involved could help towards audio compression. And finally, more recently, Kai and co-authors presented a scalable and efficient deep autoencoder towards speech compression. And this latter work relates closer to what we present here, as the architectural design and improvement are the centric point of our paper. So outside the scope of our lab, WaveNet presented their highly efficient generative model of raw audio waveform. So a model which returned impressive results, both in terms of quality and the amount of compression involved in generated speech. The model, however, only applies to speech signals and does not perform really well in real time due to its substantial size, around 12 million parameters. So while all these approaches show promising results, they seem hardly feasible and practical for non-speech signals, such as music, due to the increase in bandwidth complexity, for example. And it is to note that none of them have been able to outperform the MP3 format on audio coding, both in terms of compression as well as perceptual quality. So as far as HARP-Net goes, we explored the use of autoencoder towards neural audio coding. So what a traditional autoencoder does is that it transforms an input into a latent space, here denoted by the code vector Z, and that by means of downsampling operation throughout multiple encoding layers. So the code vector Z will then be recovered through decoding layers. And in an ideal scenario, the weights of these decoding layers would simply be inverse of the encoding layers. And that would allow for a perfect reconstruction of the latent vector Z into the original input signal. This is not a realistic scenario, and it is not achievable. This is mainly due to the accumulated error rate induced by each of these decoding layers. A residual error, which is usually introduced at the very first layer of the decoding layer, so meaning the closest to the bottleneck. And this error keeps building up until it reaches the network output. So this means that in a mirror autoencoder scenario, we treat the output of each of the decoding layer as a reconstructed surrogate of their encoding layer counterpart. And each of these outputs contains some level of residual error, which will accumulate throughout the output of the network. So fortunately, this UNet architecture, which was introduced around 6 years ago for medical image segmentation application, addresses this issue of error reconstruction by introducing the skip connection layers. And in this work, we propose an adaptation of the UNet architecture specifically towards neural audio coding. So one of the main reasons UNet architecture works much better than its traditional autoencoder counterpart is the fact that it proposes identity shortcuts, or skip connection, which pass identity information from the encoding to the decoding layers. So this skip connection can drastically help the reconstruction process and reduce the error in the output of each of the decoding layers. So in an ordinary autoencoder, x of L-1 would be estimated by embedding x of L into a decoding layer, which would then produce an estimate x of L-1 with some level of residual error added to it. So if x of L itself already contains some error by being an output of a previous decoding layer, the error would naturally accumulate across the layers and then be reflected into the network output. So in the case of UNet, considering that we directly inject information from the encoding to the decoding path and embed that information along the estimate of x of L, we thus manage to obtain a much better estimation of x of L-1, thanks to this identity information passed by the skip connection. So unfortunately, UNet, as it is presented now, does not qualify as an audio codec since it passes uncompressed information from the encoding to the decoding layers. Therefore, the skip connection, as presented here in the original UNet architecture, sort of defeat the whole purpose of what a neural audio coding system should do. So in this view, we propose to replace the original skip connection layers proposed in the original UNet architecture with smaller subsidiary autoencoders. So the resulting architecture could be treated as an audio codec since it actually encodes and compresses information that is passed from the encoding layers to the decoding layers. As far as performance goes, we can still take advantage of these identity shortcuts by means of encoding them into code vector Z and decoding them back into their estimate form. So these smaller autoencoders can be compared to the mirror autoencoder that we previously discussed, at the exception that it is now applied at the more granular level by means of incorporating these into these skip connection layers. So in this paper, we essentially prove that this type of model works better than using a single autoencoder. And as far as scalability goes, we can control the target bitrate of the network by observing the entropy of each of the code vector from Z1 to ZL. We will discuss that in the next slide. And it is important to note that this multi-autoencoder paradigm is fairly flexible, as we can apply it to essentially any autoencoder-based architecture. So now, as far as entropy control goes, it can be broken down into 4 different steps. The first one, at the nth skip autoencoder, we quantize its input y to the n and turn it into z to the m vector, which we perform scalar quantization on, meaning that an element of the y vector is replaced with the closest mean value of the 32 different means in the reconstruction y bar. So each element of the code vector z encodes the index to one of the 32 possible means as a 5-bit bit string. And this code assignment is done smoothly in the middle of the network training by employing that softmax function that sort of classify each of the y element into their corresponding quantization value. So in this context, the use of the softmax is sort of a smooth surrogate of the hard quantization. In the second stage, if we looked at Z's entropy, we can compute the lower bound of the bitrate, which correspond to the bitrate of the nth layer code, because we'll use Huffman coding to convert the 5-bit bit string into the variable length bit string. And as you can see in the equation, the entropy of the code is defined by the probability of quantization means mu to be selected during quantization. So a low entropy or low bit rate, for that matter, here means that there are very few popular mu values, while most of the other means are not frequent at all. And this would result in a very, very spiky normal distribution, which is optimal for entropy. So finally, we compute the global entropy of the system, which is just the sum of all the layer specific entropy values. And we use this global entropy during training as a way to regularize the system entropy, or more specifically the bit rate in this case. So if we want to train a system with a specific target bitrate, we simply adjust the regularization term contribution accordingly during training until we are satisfied with how well the estimated target estimated system entropy matches with the target entropy. So now for the model training, we evaluate our approach given two different use cases, given a bitrate of 40 kilobits per second, a bitrate of 64 kilobits per second. So it is to bear in mind that 16 kilobytes are attributed for the LPC operation. So for evaluation, we look at several of our model performance, each of which including additional skip connection autoencoders. And we can notice that due to the increase in the number of parameters depicted by these additional skip connection, and in order to draw a fair comparison in performance, we also present a multiple baseline system, each of which representing different network sizes that attempt in matching as best as they can their HARP-Net counterpart sizes. So for our experimental results, we measure the performance of our network in terms of signal-to-noise ratio, SNR, first. And we can see that there's an increase in performance across both use cases for all skip connection autoencoder scenarios for our models. So looking at these plots, there's no question that the addition of these additional skip connection help in both coding as well as the reconstruction of the signals. It is, although, hard to draw solid conclusion as for which of these skip autoencoder really contributes to the overall performance of the network, as there's a fair amount of fluctuation in performance across these various models. So we speculate that the bottom-most skip connection layer is the most helpful, since it is at this stage in the network that the error is the most prominent. So in other words, the earlier we reduce the error in the decoding path, the less chance there is of it propagating and accumulating. So having skip connection at this stage could really help in the reconstruction of the signal. So there's three low-hanging fruit as far as potential improvement goes. The first one would be to run this signal at a lower sampling rate, for example, 32 kilohertz, which is still a fair sampling rate for music and could potentially improve the network's performance. The second one would be to reduce the LPC, which is currently taking 16 bits in itself. So we could potentially reduce it down to 2.4 kilobits per second, which is feasible. And finally, as per some of the previous work discussed at our lab, we could potentially include a perceptually motivated loss as part of the HARP-Net. In addition to the objective results, we also provide subjective scores by the means of Mashra test that we've led on 9 different participants. So we can see that our proposed system does not outperform the MP3 format. We can see that it does not revolve too far away from it, though. And we also observed that the system, the subjective scores returned by our low bitrate HARP-Net almost reach the high bitrate baseline, which is fairly promising, considering that there is still potential future improvement that we discussed earlier. Thank you very much. HARP-Net is an open source project. You can find the code of the experiment at the following GitHub link. We additionally present some audio examples showing how HARP-Net performs against its baseline at the following link as well. Thank you.